Hello, everyone. My name is Ilse María Hernández Romero, and this is a collaboration with Profesora Lucy Teresa González Hernández from Tecnológico de Monterrey, Professor Boris Carizó from Universidad Autónoma de Nuevo León, and finally, Karina Hernández Romero from Universidad Michoacana de San Nicolás Hidalgo. And we are going to present our work titled as a multiscale modeling to optimize the selection of adsorbent material in CO2 capture. So pressure swing absorption is a technology that shows a great potential for direct CO2 capture, although its efficiency is directly related to the diffusion behavior. This work presents a simulation and optimization approach to maximize the CO2 capture from atmosphere. And simultaneously, we want to minimize the operational cost by using a packet bed of PCA column with zeolite 13X as the absorbent material. This system is compound with two beds and four stages. The pressurization, absorption, despressurization, and regeneration. This research pretend to develop a robust mathematical model considering three scales of modeling: macro, meso, and micro. However, it's important to know that to try to solve this model, we use Newman and Dirichlet boundary conditions and in order to define our problem and establish the relationship between operation cycles and the levels of modeling. In addition, we use definite difference method to discreticize the spatial domain, while orthogonal collocation is used for the temporal domain. Finally, we obtain the results in order to demonstrate that this kind of tools can help to determine the operational condition of this kind of technology. Conditions or variables like temperature, pressure, and dynamic concentration along the bed. So the motivation of this work is, according to this quote, that is the carbon dioxide problem is the defining problem of our life, of our existence. So clearly we need all the help that we can get. So in previous works that we have, we present this technology that is used amine to CO2 capture. In this case, we have just two columns. One is for absorption and the second one is for desorption. So in this case, it involves a chemical reaction that is so complex to model. And in addition, it's so expensive because we use a regeneration stage that it involves high energy expenses and high cost. So however, in this way, we explore another technology that is pressure swing absorption that is used to CO2 capture from the atmosphere. So in this case, we are modeling this technology, as I told you, as a multi-scale problem. The first scale, we consider all the column. And the second scale is we consider the particle. And finally, we are modeling the pore. So we are coupling all of these stages to try to get a robust model through all the scales in this kind of technologies. So this technology works in four stages. The first is pressure. The first stage is the pressurization. In this stage, we have the inlet of the feed gas. And in this stage, we increase the pressure in order to try to maximize the CO2 capture here. In the second stage, the CO2 is captured. And the next stage, we start to decrease the pressure in our column. And finally, the regeneration stage, that in this case, we use nitrogen as a pure in order to separate our absorbent material from the CO2. And this is our problem statement. So what is our goal? Our goal is try to determine the optimal operating condition using different absorbent materials. So we pretend to consider high absorption capacity in our model, low energy consumption, low cost, and lower environmental impact. So in this way, we pretend to use this kind of mathematical tools to evaluate different materials, absorbent materials, according to their properties. So to evaluate all of these goals that we have. So here in this part, you can see our model. This is a part of our model with the main equations that we consider mass balances, energy balances, and the coupled equation that we use the continuity equation to link mathematically talking or scales. So in addition, we consider the pressure drops because, as you can see, the pressure swing absorption works with the pressure increasing decreases pressure. So our objective functions, when we talk about optimization, that we have an optimization problem, we need to define a set or a single objective function in order to evaluate or in order to fix or weigh or goal, whatever. So in this case, we pretend to evaluate different objective functions. The first one is the power objective function, that in this case, we need to maximize the recovery CO2. And the second one is about recovery impurity. So, and one of the main is try to minimize the total cost. It means we are considered operation, maintenance, and capital costs of these in order to consider all the framework. So here I show you our boundary conditions that we use to link each stage. And as you know, when we are working with partial differential equations, we need to define some boundaries condition and additionally initial conditions to fix or try to keep our boundary and try to looking for the best solutions. Part of our results are showing here. We present the profiles along the bed. This is the CO2 concentration profile of the column. In the first plot, you can see when we start the pressurization in the column, the concentration increase. It means like the CO2 capture start. So when you get the maximum CO2 capture, it means like the adsorbent is not able to absorb more CO2. It means that the pressure swing absorption start to decrease the pressure, and the process of separation of the CO2 start. And finally, when we start with the purge, the CO2 capture starts to separate with the absorbent material. So that's the way that the profile of results show this behavior. So additionally, we obtain the operational conditions, the temperature, the pressure along the bed, and you can see the same behavior, the pressurization, the maximum absorption, and finally the despressurization. So you can see the behavior and it's the same. So however, as you can see here, we have a huge problem. We have 202,000 variables, and this is a nonlinear programming model. And we use IPUT as a solver, and the time to solve this problem was 1.5 hours. We use JuliaJump as a language programming. And we have some troubles here in order to solve because it's a huge problem. And in order to try to solve this problem, we use additional tools as a machine learning. So why we solve this mathematical model of first principle in order to create a database with all the operational conditions that we need. And after that, we develop this model based on machine learning. So in this plot, you can see some of results that we show the CO2 concentration profile of the column using machine learning. So what is the main advantage? Try to solve as a machine learning instead of first principle models, that here we can obtain some operational conditions just with data instead of try to solve all the equations involved in this process. So conclusions, the novelty and relevance of this proposal is that we are considering a dynamical model in order to use these tools to try with different absorbents and using modern optimization techniques. And this is a more robust model considering this as a multi-scale model. So the use of new efficient absorbent materials for CO2 capture and the determination of optimal operation profiles and process design, all of these to design more efficient and economical profitable CO2 capture process. So this is all, and thank you very much for your attention.